in problem 5.21, we have a block. It looks like this, and the angles of the two sides of the block are given. This angle right here, which I'll call theta 2, is 20 degrees, and this angle right here, I'll call that theta 1. That's 60 degrees. And what's asked is if I have a pulley in which this mass and this mass are in equilibrium, and they're not accelerating, they're not moving at all, then what must be the what should the masses be? How should they compare so that this thing does not accelerate? This will be M1 and this will be M2. Now, we're ultimately going to need a free body diagram, but we really need to show the forces here. Some may be necessary and some may not be, but I know that we're going to need the force of gravity on mass 1, and we're going to need the force of gravity on mass 2. Both of these will be held in place by this cord up here, which has a force of tension on both sides pulling up on the blocks. We're going to need two free body diagrams, and I'm going to indicate the free body diagram for this object right here. This right here is the x-axis, and here's its y-axis, and over here this is the y-axis and this is the x-axis. There will be a normal force here, Fn, on block 1, and there'll be a normal force here, Fn, on block 2. But I think really we're not going to have to worry about the y direction at all in this problem. I think we can solve this problem by just looking at the x-axis forces for both the individual blocks. The given is that theta 1 equals 60 degrees and theta 2 is equal to 20 degrees. And basically what we want to know is M1 and M2, and actually how those two are related. All right, now in order to be able to really work with these, we got to draw the free body diagram for both masses. So I'm going to start off with mass 1, the one on the left, and show its forces. Now it's going to have a force up the incline of Ft. This is the x-axis, this is the y-axis. And it's going to have a force of gravity, Fg1, at an angle theta 1. And you can see that up here. It's hard to see this, but if I extend this down, you can see that angle right there is theta 1. There's a normal force, but there aren't any other forces. There's no friction or anything like that, okay? So the force of tension is pulling it up. The force of gravity is pulling it down at an angle with respect to the y-axis. Now, basically, the free body diagram of the other one is very similar. This will be M2. In the negative x direction, there's a force Ft. And then down from the well, let's make this angle. Let's extend the y-axis down. Here's theta right here. And so here's how we'll draw Fg2 with its angle theta 2. And we better, okay, there you go. Then we have the normal force on 2. And of course, this is the y-axis and this is the x-axis. So there's the two free body diagrams. We need it for both. We have two masses. And let's see, we can kind of look at this and tell what our theory is, because they're both going to remain at rest. The acceleration of 1 equals acceleration of 2 equals 0. They're not going to accelerate. And since there's no acceleration, then they're in equilibrium. And if I just sum the motion along the x-axis here, the sum of the forces in the x direction on the first mass, they must add up to be 0. And the sum of the forces in the x direction on mass 2 must be 0. So that's really all we need to solve these problems, because we really want to know how the masses compare. And that would be dependent upon the x component of the force of gravity on both the blocks. So my solution is simply just to add up the forces. Okay, so if I add up the forces on mass 1, okay, then Ft, this is just in the x direction, okay, Ft is pulling it in the positive direction, but the x component of Fg1, okay, those two must add up to be 0. And then if we do the same thing for mass 2, now in this particular case, Ft is negative, so minus Ft plus Fg2, there's its component in the x direction. Those must add up to be 0. If I add these two equations, then Fg2, if I add these two together, the Ft's go away. So Fg2 in the x minus Fg1 in the x must be equal to 0. Now we can put in the two we put in the force of gravity for both of these, which is mg. Let's say I think I can start up here at the top right here. Really don't need a whole lot of room because we're pretty near finish. Fg2 in the x direction is mg, or m2 times g, m2 times g, and then its x component is Fg times the cosine of theta 2. Okay, I'm going to move the FBD over here so I have a little bit of room. Okay, that's got to equal the x component of the force of gravity. See, I'm going to solve this for the other side of the equation. That's equal to m1g cosine theta 1. So sorry about this running together like that. Okay, so you can, I think I'll just leave you with this. Okay, but you can see that you can find the ratio of the masses. As a matter of fact, why don't we state that the unknown is the ratio of m2 to m1. You can see writing it that way lends itself well to finding the ratio of the two masses in terms of the angles, okay, the functions of the angles right there. So let me clean this up a little bit right here. Okay, and so you can solve this for that ratio and you'll be finished with this problem.